Okay, so this is term 2, week 3, Physics CA, from 4.1.4 to 4.2.4. But for the sake of finals, I'm gonna start at 4.1 because I know people would like to go back and watch the notes. People did that for the last finals. So if you're watching this for the CA, go and skip till, I'm not sure. Hold up. Go and skip till, I'm not really sure, but and it doesn't really make a difference. And it's just 4.1 point الcoil, you don't need it. Hold up. Okay, you can skip till here if you're watching for the CA. Okay, but I'm gonna start over here. Okay, chapter 4, it's about changes in flux. We start with a magnetic force acts on charges only when they are moving, that is a stationary charge experiences no magnetic force. There will always be a force on anything, okay? But we're saying that there will be a magnetic force on any object that has motion, okay? But if it's stationary, if it doesn't move, it doesn't experience a magnetic force. But electric force, of course, gravitational force, of course. But other than that, there's nothing, okay? If it's just stationary. If they ask you in space, there's always no force because there's no force in space, okay? They don't really ask these questions, but you need to know this, of course, if you're doing IG physics. You should know that a force exerted on a current only if the current is not parallel to the magnetic field, and that force has maximum magnitude when it's perpendicular to the magnetic field. Remember, I, B, F, alright? A force is produced, it's exerted on a current magnetic field, I and B, when, if it's not parallel. If it's parallel, the magnetic field and the current, then what's going to happen? There's going to be no force, right? You can even use the IBF right-hand rule. If they're going in the same direction, you won't have a force, mustahil, right? If they're not parallel, then the force does not equal 0. And if I and F are perpendicular, then you're going to get the maximum amount of force. Okay, so you can have, you can see questions like this. مثلا, these are just some questions from last year, like this one over here. When it's parallel, no force is exerted. When I and F are perpendicular, you have to use the right hand rule to see that it's actually outward and going there. Okay, and then here upward, because when I and B are when they have like this is over here. See, when I and B are they have an angle, F will be upwards, right? Well, is that outwards? Yeah, that's upwards. Okay, so when they have an angle I and B, F will be upwards. Okay, when I and B, oh, this is I and F. Okay. This is hold up. This one's obvious how there's going to be upward force because it's going to be like this, right? But here, I and outward force, I think they meant to say B, not F here. Okay, this should have an outward force like this. Okay, that's how it should be. Okay, let me erase all. I can't. Okay, anyway, yeah, these are just past questions. وكمان I saw one. Okay, no, that's the only one. Let me continue. So you just need to know these assyria if they come. If you force a wire into perpendicularly inside the magnetic field, a current will be induced in this wire and the positive and negative charges will be separated. To find the direction of the current, you can use Fleming's right-hand rule, FBI. It's the same thing as IBF, but instead of having your first finger as the current and your last finger as the force, you just swapped F and I. So you're gonna, basically how it works is you have a wire, okay? Okay, and you're putting a magnet in. I think it's here. Let me show you. Basically here, okay? Let me remove this. Look, you have a coil, a wire. You're moving the magnet in. If you're moving it in north, you need to memorize that north going in, it's gonna cause a clockwise deflection. Okay, memorize north is clockwise. Only for this exception, huh? But if it was like the letter rule, you guys know north is counterclockwise and south is clockwise. But anyway, if you're putting the north in, it's gonna cause a current to be produced. So the galvanometer will give you a reading and it's going to move clockwise. Okay. If south was moving in, why this one's wrong is because this one should be going to the left. Okay. What they did is they gave you the direction of the current, which is clockwise, and they want you like, to choose the correct one. Obviously, you should be moving the magnet in, so you're going to be exerting a force. There is a magnetic field because there's a magnetic field in between the coil and the. It's an electromagnet. It's turned on, right? It's a coil connected to. It's like there's a magnetic force. So there's a B. So you have F, you have B. So what are you going to end up with? You're going to get a current. Okay. So same way when we used to get when we used to put a current and a magnetic field, it would give you a force. Now if you put a force and a magnetic field, you're going to get a current, but it's a sensitive current. Okay. Moving a wire at a constant speed v in space and in the absence of a magnetic field requires no force, but making it through a distance in a magnetic field obviously requires a force. Okay, that makes sense. If there's no magnetic field, there's no force. If there's a magnetic field, there's a force. And this is very important here. When you change the flux through a loop, the current is induced in the loop. Flux is defined as the strength of the magnetic field to a certain area times the projection of the area normal to the field. Flux theta is flux phi is equal to BA cosine theta. Okay, sometimes they might just say BA, where A is the perpendicular area. Okay, and that represents A cosine theta. Okay, so when the flux changes, current is induced. So enter you only get an induced current when the flux changes. Okay, that's when you get an induced current. And we continue to talk about it now. This is where, this is a bit bad. Okay, so why I put very important on this, because it came as a previous question. The current can be caused. How do you get a current? By a change of magnetic flux through any surface bound by that circuit. Okay, see here. So when the flux changes, current is induced. Okay, so it can be caused by a change in flux. State and describe where it is. Okay, a current from left to right will be induced. What was it? Okay, yeah, this is basically we're explaining the coil. When you put the north inside, a current from left to right will be induced. So remember the clockwise reading on the galvanometer, this one. Okay, but if you were to no current will be produced, no motion magnet. Yeah, then basically what they ask you is if you put in the north of the magnet into a coil, what's going to happen? There's going to be a current induced from left to right, in other words clockwise. Okay, and then they said, what if there's no motion of the magnet? Okay, like what if the magnet's at rest? Obviously there will be no current. Why? If there's no motion, then there's no force, and if there's no force, can you have current? No, because F be I, right? You need F to have I. The current from right to left. Okay, now if you put the south pole first, the current's going to go from right to left. So the direction of the ammeter, of the galvanometer, will go it's going to go counterclockwise. So it's going to go the other way around. This is why here this was wrong, because this is supposed to be to the left. Okay, it should be counterclockwise. Okay. The induced EMF depends on the change of flux. Induced EMF, whenever you see induced EMF, it's related to the induced current. Okay, so don't get confused. The induced EMF, what does it depend on? Remember, we're talking about if you put a force in a magnetic field, you're going to get an induced current, and that basically means you're getting an induced EMF. Okay, what does it depend on? The change of flux. If there's more magnetic field, then there's more EMF. What does the flux also depend on? The motion of the magnet. What does the induced EMF also depend on? The motion of the magnet, the force. The galvanometer will produce a faster reading if there's a faster force. Remember, F, B, I. The induced EMF and current, when do you get it? Depending on the force and the magnetic field. Higher force, higher EMF. Higher flux, change. Remember, I'm not telling you magnetic field, I'm saying change in flux. So D phi. Okay, there's an equation for it later. We'll talk about it later. So always remember, what does the induced current depend on, or the induced EMF? What does it depend on? The change in magnetic flux and the force, which is also somewhere here. Over here, I think it's just this one. It's just the same. We're just repeating ourselves. Now, the flux. How can the flux be changed? By using a more powerful magnet or increasing the number of turns in the coil. We know this, right? You remember, magnetic flux is equal to BA. if you increase to increase the magnetic field, the strength of the magnetic field, how do you do that? Just use a more powerful magnet. If you want to increase the area, just increase the number of turns, because there's now more surface area. Very easy. Now we start with okay. Here was this is the start of what you need for the CA for week 3. Yeah, how can the flux be changed? هلا Faraday's law. Okay, basically a guy in like 200 years ago, he was like playing around with magnets. Okay, and he was like, shit. When he played around with a force in a magnet, he started to get a current and induced EMF. And he was like, shit, okay, the induced EMF and the current is directly proportional to the rate of change of the magnetic flux. Okay, so EMF, induced EMF, is directly proportional to the flux. There's an equation for it, okay? And he concluded 3 things. The faster the magnet is moved, obviously the larger the current, because the faster it's moved, and there's more force being put in. Remember, FBI. So to get a larger current, you need a larger force. So the faster it moves, there's a larger force, which means a larger current. The more powerful magnet, FBI. Remember, if you're using a more powerful magnet, you're increasing the strength of B, so there's going to be more current. More turns. Remember, the change in magnetic flux, more turns, there's more magnetic flux, right? So larger current, okay? So he came and he wrote for us a nice equation. E, this weird E, it's like this, kind of looks like the sigma, okay? It's called the induced EMF, okay? It's equal to N d phi over dt, okay? Rate of change of magnetic flux. Remember, induced EMF is directly proportional to the rate of change of magnetic flux. Remember, math, what does rate of change mean? It's a derivative, okay? So, they won't ask you this equation, but it just helps you remember, okay? So, the induced EMF is directly proportional to the rate of change in magnetic flux. So, Faraday came and said, okay, there's now, you guys, whenever you play around with the magnetic flux, you're gonna get an induced EMF. Okay, then Lenz was like, shit, okay, you told me there's gonna be an induced EMF, an induced current. Okay, طب, in what direction? Okay, thank you for telling me there's induced EMF, there's induced current, but I don't know, like, is it gonna be to the right, is it gonna be to the left, is it gonna be down, is it gonna be up? So Lenz came and he's like, okay, let me prove what direction it is for you. Okay, so Lenz came and said, he's like, current, okay, the induced current, it's gonna flow in such a way that it opposes the cause, which is the inducing current in the coil. The induced EMF tends to oppose the change. Is that charge? I don't really see the change producing it. Okay, this is basically the law, and it's over here. The law stating that the induced EMF opposes the change of flux is known as Lenz's law. You must memorize this. Okay. What does this mean? Let's say you have a coil. Okay, we're gonna go back to our lovely explanation here. Okay, you're going in. What's the induced EMF gonna go? It's gonna take you back out. It's so simple, so simple. Okay, so the current's going in. It's gonna go like, oh shit, I'm gonna push you out. But now, as you're going out, there's gonna be smaller magnetic flux. It's gonna be like the magnetic flux is gonna be changing, so it's gonna be going out. So the current is gonna be like, no, wait, don't go out. Come back in. So it pulls it back in. And then as soon as it's starting to see it go back in, it's going to be like, no, you know what? Get out. So it always opposes the motion. So by the way, if you try this experiment and you get a coil and a magnet, and you try like getting this magnet and try putting it through a coil, there's going to be a lot of resistance. You need to like you actually need to put in a force. You know what I mean? So that is due to Lenz's law, because the induced current will oppose the flux. Okay? Lenz's law, he basically took Faraday's law and he put a negative. Okay, so just to say that it's opposing the change in magnetic flux. Okay, so inducing EMF tends to oppose the change producing it. The change, what produces the induced EMF? The change in magnetic flux. And please, we're saying change in magnetic flux. We're not saying magnetic flux. So why is this significant? Because like I saw someone explain this. When I tell you change in magnetic flux, okay, let's say you started here at 0, and then when you went in, it's like 5, okay? And then you were like, okay, here 5, and then you finished here at 0, okay? And I tell you, okay, which one has a higher induced EMF? They're both gonna be equal, okay? Even if we're talking about when the magnet is over here at 5 and when the magnet's over here at 0. I'm gonna tell you they're both equal, okay? It took both of them 5 seconds. Why are they both equal? Because I'm not telling you how much magnetic flux you have. I'm telling you for the change in magnetic flux. Here it changed by 5, and here, even though you're going out, it's still changing by 5. Okay, this is like, these are questions you might ask. Okay, it might ask you, what does the induced EMF depend on? And some people put magnetic flux. That's completely wrong. It has to be the rate of change in magnetic flux. طيب, let's see. As a coil is pulled out, the flux decreases. According to Lenz's law, the EMF will oppose this decrease and will pull the coil inwards. Okay, this is just elaborating on Lenz's law. You're pulling the magnet out of the coil. The flux is going to start to decrease, and since Lenz's law basically, Lenz's law says, it always opposes. Since you're pulling it out, it's like, no, come back, I want you back in my house. Okay, so it comes and it pulls the magnet back into the coil, and then after you're starting to pull it in, again, the flux is going to start to increase. And Lenz, this guy, he's always like this negative person. Whatever you do, ما بيعجبه. Okay, the current is always like against what you do. So if you're going in, he's gonna be like, you know what, nah, get out. I don't want you coming into the coil. Okay, I think خلاص, you guys got Lenz's law. These are just the grids. Please make sure to solve them. Grid, it's 1, 2, 3, 4, 6 grids. I think these are them. 3, I did 5 here. I don't know, 159, 160, 161, 162, 163. Yeah, I'm missing two grids here. Make sure you do them, unless I solve them maybe later. Did I solve anything? No, I didn't. Okay, please make sure you solve the grids. I'm not gonna go over them, but please make sure you solve them. Okay. Let's see. Describe the way to induce alternating currents and present it mathematically. Okay. Hold on. Current. Okay, yeah. This is where it starts to get a bit interesting. Okay. Yeah. Current can be split into DC and AC. DC being direct current and AC being alternating current. From the word DC, from the word direct and alternating, you can kind of tell which is which. So, and if I gave you a graph of direct current, this is how it looks. It's just 4 ampere مثلا. Okay, بس نحن always when measuring current, we for some reason we look at the EMF, we look at the voltage. Okay, so if I were to give you a VT graph for when I say VT, I don't mean velocity, I mean voltage. Direct current, it will be a straight line. Alternating current will be like this. We call it a sinusoidal graph, but it's not necessarily sinusoidal all the time. Okay, what's the difference between DC and AC? DC, the current flows in one direction. In AC, the current flows in 2 directions. So in DC, it's our normal from positive to negative, our normal current. But in AC current, this is how it looks. It moves in both directions at the same time, with this being your power source. So you need to know this. When the loop is parallel to the magnetic field, while it's rotating, the rate of change through the magnetic flux is maximal, and the induced EMF is maximal. This is a must. This is why I told you before. Remember that the induced EMF doesn't depend on how much the magnetic field is. It depends on, as the magnetic flux, not magnetic field, it depends on the rate of change of the magnetic flux. When it's parallel, I'm sure you guys remember, you have the plates here, right? It's the same motor, okay? When it's parallel to them, right? Something like this, okay? When it's parallel to them, we know that the magnetic flux is equal to 0. But like I told you earlier, it doesn't depend on how much the magnetic flux is. It depends on the change of magnetic flux. Because before it was parallel, it was how much? It was perpendicular, right? It was maximum. When's the magnetic flux maximum? Hey, it kind of looks like this. So I don't know. Like imagine perpendicular, right? When it's perpendicular, the magnetic flux is maximum. So let's say it was like 20 and it rotated. It became now flat. It's now parallel and it's 0. Right? So from 20 to 0, that's a big change. So remember, we don't depend on how much the magnetic flux is. We don't care about the value. We care about the value of the change. By how much did it change? Okay? So when is the induced EMF maximum? People will say when it's perpendicular. No, that's for DC. That's for DC. We don't care about DC. We're talking about AC. Okay? For AC, it's alternating. Okay? Remember, the induced EMF changes. It constantly changes. Okay? For that reason, it's maximum when the plates are parallel to the magnets. Okay, when the loop is when the loop is parallel to the magnetic field. Okay. The induced current, okay, I don't think you need to know this. I doubt you need to know this. Let me see. Let's check. If it wants to load. Okay, yeah. So it's in the blue. It's as blue text, so that's why I wrote it. Basically, the induced current. I doubt you need to like apply this formula because it wasn't in any questions that I've seen. But you need to know what the formula is in case they ask you multiple choice. I max sine 2 pi f t. Okay, why? When we see sine, you're thinking sine function. Remember, we're talking about alternating current. Alternating current is kind of like a sine function. Okay, it reaches I max over here, which is the highest, and this is over here negative I max. Please don't call this I minimum. We don't call this I minimum. I minimum is 0. It's over here. Okay. Because sometimes current, when it's negative, it means it's flowing in like the direction that we don't want. It's flowing in the negative direction. Anyway, I is equal to I max sine 2 pi ft. Sine 2 pi ft is basically sine 360 ft. Just know this if you see it, okay? Yani take it, just showing that it's a sine function. The IT graph for an alternating current, like I told you, it's like this. It's a sine function, okay? And these are just very easy. Root mean square. Root mean square, you don't really need to know anything other than the root mean square of the current is just equal to the current, the maximum current, divided by square root of 2. Okay? So to find the root mean square of anything, you just divide the maximum value of that thing by square root of 2. Okay? And then IRMS is I max over root 2, VRMS is V max over root 2. And this P max, I think my physics teacher was just trying to act smart. I don't know if it's actually in the book. Yeah, it's not in the book. I don't think. I can't. Yeah, he's just trying to act smart. But I wrote it down on my copybook. If you want to know it, power max is equal to I max times V max. So power, what's this? Power average is equal to VRMS times RMS. Okay, so average power is VRMS I. Okay, they don't ask this shit. Okay, you need to know this. T is equal to 1 over F. This T is not time. It's the period. Okay, period as in the time for one revolution. Okay. إذا أنا قلت لك, let's like go back to our I graph for the AC. This is one period, right? Because it's one complete revolution. صح؟ طيب, let's say أنا وقفت لك هون at 4 seconds. يعني T is equal to 4 seconds. Okay? و F هي شو? F is frequency. F is how many rotations does it do. Okay? Okay, here we have the principle of the AC generator. But I'm surprised I didn't solve any questions to do with Hertz or she. I remember solving in the class. I'm surprised I don't have anything in my book. The principle of the AC generator. Okay, this is now how the AC generator works. But before, like I'm sure I solved some questions to do with, yeah, like here, stuff like this, and we're gonna see them in the quiz anyway. Anyway. So we have now the AC generator. And I'm gonna refer to the book to show you some graphs, but I want to, the bullet point stuff, I'm gonna read out from my notes because this is the important stuff. How an AC generator works is very similar to how the DC generator works. You have the North Pole, South Pole, and you have a coil, okay? But here's the thing. The difference between them is that here it's an alternating current, and in the DC, it's a direct current. Forget about this over here. We're looking here, okay? In the direct current, you're giving it a current and the coil starts moving. In the alternating current, you're giving a small current to push it, and then it's going to produce a force in a magnetic field which produces a current. Remember FBI, but DC, I like to think it uses IBF. This is how I like to think about it, okay? AC, you're using the fact that force in a magnetic field gives you this current, which changes depending on how much force and how much change of magnetic flux. And DC, it's kind of like this fixed value of current that you attain all the time, and it just starts rotating. What's different about the alternating current? I'm going to start first with the direct current that we did in term 1, right? I don't care about this top one. This top one's AC. Remember, we had our split ring commutator. We had a positive side and negative side, and it would just keep on alternating because we'd want it to flow in one direction. صح? Okay, that was DC. بس هلا alternating, what do you have? As the coil rotates relative to the poles of a magnet, the flux through it varies, right? The magnetic flux begins to change. An alternating EMF is induced across the coil's ends, so an alternating current is generated in the coil. Why is an alternating EMF induced? Because the flux changed. Whenever you change flux, remember an induced EMF is caused or created by any change in magnetic flux. So you change magnetic flux, صار عندنا alternating EMF. What does alternating EMF mean? Induced current. Very easy, alternating current. The direction of the current changes twice every revolution when the coil is normal to the magnetic field. So it changes over here. When it's normal to the magnetic field, or not here, this is parallel, right? Because the magnetic field goes like this, okay? When does it change? It changes when, I don't know why مش جايبين لي graph, but it's when like it's normal. When it's normal يعني مثلا when it's like this. Okay, wait. I'm gonna try and you get me? So it's going like perpendicular to it. Okay, when it's normal, that's when the direction changes. Here in AC, the direction of the current changes twice every revolution when the coil is normal to the magnetic field, and alternating current is generated. Slip rings take that alternating current to the external circuit. Okay, over here you have things called slip rings. Okay, slip ring commutators. Okay, they have these brushes fixed to them, and basically they take the current, the alternating current, and they just take it to the external circuit. Okay, and if you want, like, there's a video here. I'm gonna watch it just to see maybe there's like something I can add to what I just explained, and I'll get back to you because this stuff usually takes a long time to load. Okay, so this still hasn't loaded, and I'm kind of impatient, so I'm gonna just skip it. Anyway, so we're done now from the AC generator. Very easy. Instead of having a split ring commutator, we have two slip rings that just take this induced current and just take it outside. And I can't really think of anything else that I can add. Some questions, like, you're going to see questions where you have to use مثلا T is equal to 1 over F. Yani, this is normal. You're going to see these types of things. But let's continue. The principle of a simple DC, it's very easy. Everything here is... yeah, everything here is just talking about how DC is, you have the same direction of current. It's a direct current which has its same direction, and for that reason you always have the same value of current. That's all they're saying, and we know how it works. We have a split ring commutator that changes its direction every half a cycle. Okay, you need to know two things, because they ask this. You see these two graphs, you need to understand them. How do you know what this is? Is it going up and down? Does it fall down into the negatives? Yes, so that means it's AC. So which one will it be? It's obviously going to be this one. Why? Because you choose the one that has two slip rings. How do you know which one's AC? Well, how is AC different than DC? AC has two slip rings. DC has a split ring commutator. Okay? This one here, when it stays positive all the time, معناتها it's DC. Okay? Like this نكون خلصنا notes, so let me just start with the quiz. It should be very easy. An experiment is performed to demonstrate how the change in magnetic flux produces an electric current. So the flux is varied by moving a magnet relatively to the coil. What does not affect the induced EMF? Okay, if they ask you in the quiz what does not affect, نحن حافظين الريجن. He gives you what does not affect the induced EMF. He's going to get you in the exam what does affect the induced EMF. And we know over here which factors affect the induced. The speed of the coil. Speed of the coil غلط. Okay, but the speed it enters the coil. Okay, that makes sense. You see, this is how it came in the exam. Which factors affected? The number of turns in the coil, the strength of the magnetic field, the speed of and how fast it's going into the coil. Thickness of the coil is wrong, but in the quiz they said what? What does not affect the induced EMF? Okay. Question 2. A rectangular wire ABCD is connected to a galvanometer that measures the induced EMF. The wire is rotated at a constant rate inside a horseshoe magnet as shown below. How can we increase the induced EMF? How can you increase the induced EMF? By rotating the wire faster, the speed of how fast you rotate it. If you're in the regional Sabbath grade 11 group, I'm probably going to send this and just cross out the things that we don't need. These are very easy, really. So anyway, let me continue. Question 3. Which of the following statements are true? A loop ABCD is rotating between the poles of a permanent magnet and it's going counterclockwise. When ABCD is horizontal, so like this, the rate of flux change through the loop is 0. Yes, because when it's horizontal, that's when it's normal. صح? And by the way, just so you can understand. Here, if I told you, I remember telling you that it changes direction when it's normal. So it changes twice every revolution, and when does it change? When it's normal to the magnetic field. So why does it change? It changes when it's normal to the magnetic field when the rate of flux is wait, huh? Yeah, okay. Yeah, I don't know. I was getting mixed up. Basically, what I'm saying, when ABCD is horizontal, it's perpendicular to the magnetic field, right? And when it's perpendicular to the magnetic field, the rate of change of flux is zero. It's zero when it's perpendicular, but when is it maximum? When it's parallel. So if you want to see here in our graph for the AC, over here is when it's perpendicular, okay? And when it's perpendicular, by the way, it's when the rate of change of flux is zero. And what happens when the rate of change of flux is zero? That means there's no induced EMF. That's why it's zero. When it's maximum, this is when it's parallel. Okay, when it's parallel to the magnetic field. When they tell you it's horizontal, معناتها it's perpendicular. Okay, so don't get mixed up. You should know when it's perpendicular, it's horizontal, right? In the horseshoe magnet. But if it's a different thing, that looks different. Okay, but when it's perpendicular, d phi is equal to zero. Okay, when it's parallel, so مثلا I'll put the parallel symbol is like this, I think. When it's parallel, d flux is maximum. Okay, here when they're saying it's horizontal, take a look, it's perpendicular, so that means the rate of change of flux is zero. When ABCD is vertical, the current is zero. No, when it's gonna be vertical, معناتها it's gonna be parallel, right? When it's parallel, is the current zero? No, it's maximum. Okay, the current generated in ABCD is called an alternating current. Of course, it's an alternating current because you're rotating it between, when you're rotating it, you're putting in a force between a magnetic field, so you're gonna have induced I. You're rotating it. If they tell you it starts rotating by itself, and no, it's not induced, it's a direct current you're supplying to this, and it's just rotating because there's an induced force. But enter, you're rotating it. You're putting the force between a magnet. So what's gonna happen? You're gonna get I. When do you have FBI? When there's an alternating current. Okay. The current through the galvanometer changes direction twice every rotation. Remember, for AC, when does it change? It changes twice every revolution. The frequency generated in the frequency generated in the current is double the frequency of the loop's rotation. No, the frequency of generated current is the same as the frequency of the loop's rotation. Remember, they're directly proportional to each other. Okay, you double the loops, then the current will double. Okay, question 4. In which of the following electric devices does the current change its sense? Okay, a twin ring generator and is the same as what we call a split ring commutator. Okay, and the split ring commutator changes the sense of the current. Slip ring commutator obviously changes the sense of the current. Remember, it's the AC generator. And the dynamo is correct, but they told us it's up until 4.2.4. And after the mechanics CA last week, when our captain Hani decided to get a question that wasn't in the material, and he started saying, you're supposed to know it from before, I don't trust him. He put it in the quiz, so خلاص, just know it. This is a dynamo. I'm not going to explain to you in detail because that's for next week, but just know that the dynamo, it also changes its direction. Because until you have the bicycle, it just keeps changing direction, just keeps moving. Okay, just know it. Split ring generator. Shit. Okay. My bad. When I told you split ring commutator, no, that's wrong. Okay, it just switches the connection. But remember, in the split ring commutator, that was over here, right? The split ring commutator, it was for DC. Remember, slip is for AC. The split ring is for DC. For DC, the current never changes direction. That's why it keeps on moving in the same direction. Okay? So for split, it doesn't change its direction. The whole point of split is so it doesn't change its direction. So the ones where it changes its sense are the slip ring and the dynamo. Okay, we know this. And the twin ring generator is the same as, you see the twin ring? It's 1, 2 together. Okay? That's what it is. It's also AC. So this is AC, and I think this is AC, so I'm not sure. But dynamo just changes the direction. So my bad. See, split ring generator is wrong because it doesn't change its sense. In split ring, it's a direct current. Okay, it doesn't change its sense. Okay. Question 5. An alternating current is given by the expression I is equal to 45 milliampere. So this is I max. Sine, let me see here, sine, sine 18.8 rad second time. Okay, so here you need to use the formula that was, I think it was I is equal to I max sine, I think, pi squared ft, or something like this. Pi squared f, let me see, pi f squared t squared, something like this. It was, let's see, there was no square. Oh, sorry, sine 2 pi, no, there's no square, sorry, I mixed up. 2 pi ft. Okay, very easy. 2 pi ft. Obviously, the peak value of the current, I max, is the coefficient of sine, which is just 45 milliampere. The frequency of this current. Okay, they gave us 2 pi ft is equal to 18.8 rad. So 2 pi ft is equal to 18.8 radian. Okay, so how do you find the frequency? Frequency is just going to be equal to 18.8 over 2 pi t. They kept t over here as t. Yeah, they kept t as t. I didn't see it. Okay, so 18.8 rad times t. So this 18.8 rad times t. So obviously t will cancel with t. So f is just going to be equal to 18.8 divided by 2 pi. Let's check this. 18.8 divided by 2 pi. They said use pi as 3.14. Okay. So it's going to be, sorry, I need to put this in brackets. It should be 3, right? To the nearest Haida, it's going to be 3. Okay, so you need to use, anytime you see sine and I, you need to know I is equal to I max sine 2 pi ft. Okay, even though I said it won't come بشكله خلاص, they're going to bring it, because I never saw them bring it in a different exam. Question 6. Two different methods of generating electricity are shown below. Which one's alternating? Which one is one direction? Obviously, A is going to be alternating because it has the slip rings, and B is direct because it has the split ring commutator. Okay? Question 7. A coil is rotated in the presence of an external magnetic field to produce electricity. So there's an induced EMF. The output voltage generated in the coil is shown below. So akid, we have a sinusoidal function, so it's going to be alternating. When is the surface perpendicular to the magnetic field? When we say perpendicular to the magnetic field, what happens when it's perpendicular? The change in flux is equal to 0, which means that the induced EMF is what? 0. So when is it 0? Over here at A and over here at C. When is it parallel? When it's parallel, the flux is equal to max. Okay, and that means the induced EMF is max. Please don't put B only. Like I told you, here it's the same value. Okay, it's the same value, just in a different direction. Okay, so it's parallel, gives you maximum values. We don't care about the direction, we just care about the value. When is it maximum? At B and D. Okay. Question 8. The direction of the current in the loop. So basically they gave you the magnetic field. The magnetic field is X, so it's going inwards, right? And they gave us the force. They're moving. Sorry. They gave us the magnetic field is to the left, and they gave us that the loop of the wire is being pushed into. So this X actually represents the force, which is inwards. So you have the force being inwards. You have the magnetic field going to the left. So, they want you. How are you gonna figure out this counterclockwise? Okay, so basically, for Lenz's law, you need to. There's like a new way you need to like do it. Okay, instead of using the FBI method, FBI, we're gonna use the motor rule where you curl. Okay, because FBI, it will give you the direction upwards, downwards, leftwards, rightwards. But sometimes you're gonna want the direction of the rotation, so you're gonna have to use the motor rule. Okay, and basically how the motor rule works, you want to find the direction of the current. Okay, you need to remember Lenz's law says that the induced current, the direction of the force of it, opposes the direction of the initial force. So if you're being pushed into, then the force of the current will be what? Outwards. Okay, so you're gonna start with that. You're gonna start with outwards, and then you're gonna curl in the. You extend your fingers, right? For the motor rule, you have your thumb and you have collectively the other 4 fingers. I just want to see, am I doing this correct? Now, how does it show? You have your thumb and the 4 fingers collectively. Use them together. Okay. How it works? Your thumb is the force. Your 4 fingers are the magnetic field. You're gonna take your thumb. Since we're pushing it into, the force of the induced current will be outwards. Okay. It opposes. It's Lenz's law, right? So I don't. Why am I up here? Okay. So since we're going out, finger my thumb for my force is gonna be going out, uh, and our magnetic field is going to the left. So you're gonna extend your fingers to the left. Okay. Now take your fingers and curl. What direction is this? It's clockwise. That's it. Yeah, you just curl them. Curl them in the direction of the magnetic field. It's gonna be shoe clockwise. This is counterclockwise. Okay, when you go like this, it's counterclockwise. So according to Lenz's law, here it's gonna be counterclockwise. Okay, to find the direction of any induced current, you always use Lenz's law. How it came in the sample question sheet is like this. Okay, the direction of the current here, according to Lenz's law, is clockwise. Here, they're pushing it in, so the force is going to be out, right? Now, the magnetic field is right. So curl your fingers to the right. Curl it to the right. What direction is that? Clockwise. I think you can kind of see. Hey, out. Curl them to the right. You understand what I'm saying? So out, curl to the right. It's like clockwise. You get what I mean? But it's going to be clockwise. Okay? You can just memorize if you want. But it's either going to usually be left or right because it can't be same direction as the four. Anyway, I hope you understood this. It's not that hard. But yeah. Okay, look, question 9. What's true about the simple AC generator? The AC generator, okay, you need to know the current is removed from the twin ring commutator. The twin ring is the slip ring. Why do we call it twin? Because we have two. We have one here, remember? And let me open the ebook. إذا بتروح على ebook, it's over here. We have two of them, right? That's why we call it twin. In the simple generator, the magnet rotates about a stationary coil. The magnet rotates? No, it's the coil that rotates. An AC generator can contain either a permanent magnet or an electromagnet. Sure, yeah, why not? An AC generator can contain either slip ring or split ring commutator. No, split ring is for DC. If the loop of the generator moves uniformly, the current generated varies according to a sine function. If it changes uniformly, then it's gonna look like a sine function. Let me continue it. Heck. Okay. Again, I'm gonna send this file later. Some things you might like. You like to see them. Like مثلا here, in an AC generator, a coil rotates relative to a magnet and an alternating current is generated. It's taken out through a slip ring commutator that contains carbon brushes connected to it. These guys are called carbon brushes, okay? Question 10. There's nothing here, like the magnetic force is directed, let me see this. Okay, question 10 is the same thing, repeated as question 8 or something like this. I'm gonna come back to this in a sec. So I was looking here and I saw another question like this. You need to use Lenz's law. This is not required in the oscilloscope. It's a multiple choice question. You can look at them later. Anyway, over here I was looking at this. Okay, here you need to use also Lenz's law. But people will say, how you have I and B given? How are you going to use Lenz's law? Look, you're talking about a negative charge. You're talking about a single electron. Isn't that, do you think that's enough to count as current? No, that's what we call an induced current. Okay, that's what you call an induced current. The induced current, by the way, in the book, the definition, is that it's not a full charge. It's a very small, tiny current that we count as just numbers of electrons and protons. Okay, not proton, but numbers of electrons, positive and negative charges. Okay, so when you just see one charge, you count it as Lenz's law. You need to use Lenz's law because this is the induced current. So anyway, they gave you over here, they gave you the induced charge, the direction of it is going to the right, and they gave you that inside is the magnetic field, and they want you to find the force. Now, if you use IBF, and I'm going to turn on my camera for this, if you use IBF, you're going to get that I is going to the right, B is going in, so stick F up, you're going to have now upwards. But again, what are we using? Lenz's law. So you're going to get upwards. For what are you going to do? It's going to be downwards. It's always opposing. Okay, the magnetic force on the negative electric charge is going to be opposing it. The force on the charge is always opposing because they said, look, on the negative charge. Okay, negative electric charge. Question, let me see. For 11, the peak current in the AC circuit is 20 mA. They want RMS. How do you find any RMS, IRMS? You just take I max over radical 2. And let's see, to one decimal place they want. So 20 divided by root 2. It's going to be 14.1, which is what we got. Okay. Question 12. Consider the device shown. Select the graph that represents the output of this device. Over here, you have, again, a generator. We need to know, is it AC or DC? It's always going to be DC because it's the split ring commutator. Okay, and the split ring commutator, remember, it doesn't go down. It's always DC, so it's a direct current. Okay, it has this fixed Imax value. Okay, so it stays positive in one direction. Okay, so it stays like this. It was in the book. This is why I stressed on it over here. Okay, question 13. A current is induced in a circuit. When is it induced? When there's a change in magnetic flux, right? Question 14. How can an alternating current be induced in the loop A, B, C, D? How can you have an induced current? If you keep it at rest, is there going to be an induced current? No. Remember, you have F, B, I. This is for induced current, okay? When it's one small electron, one small negative charge, one small charge, it's going to be induced current. When do you get it? When you have a force and you have a magnetic field. هون حطوا لنا magnetic field. What are we just missing here? We need a force. And how can you get a force? You can do it by moving the loop around, by rotating it. Okay? Always FBI. To get induced current, there should be a change in magnetic flux. To get that change in magnetic flux, you need to have F and B. Okay? You need to have a magnetic field and a force. Okay? Lenz's law states that the induced EMF tends to oppose the change in the what? Magnetic flux. Okay? Lenz's law opposes the change in magnetic flux because we said Lenz's law opposes the change that causes it. Okay, what causes the induced EMF? The change in magnetic flux. So the Lenz's law says that the force produced, it opposes the change in magnetic flux because the change in magnetic flux is what causes that induced EMF. Okay. The TMS, transcranial magnetic stimulation, is a medical technique aimed at treating anxiety and depression. Both conditions are known to arise from abnormalities in currents flowing between the nerve cells in the brain. During TMS procedure, a patient wears a helmet that contains current-carrying coils. The current in these coils are rapidly changing. The current-carrying coils generate obviously, if it's changing, it's a variable magnetic field. In turn, generates eddy current. What? Yeah, on God, this was not in the book. Not in the book, but like in like the section we read. I don't know, maybe he got this out of a bio book. But you guys know Mr. Hani. He could get any question. My advice to you is to memorize this. Okay, transcranial magnetic stimulation. It's basically let me read about this. Wait. Okay, so I read about this, and basically, it's actually kind of like it's nice. But they should at least teach it to us. Basically, if you have. Like you're a guy, okay, and you're depressed. You have depression, you have anxiety, maybe from school, maybe from the Sabbath system. I'm sure most of us have anxiety from the Sabbath system when it comes to the exams. But let's say you have anxiety. You're diagnosed with depression. Okay, how it works basically, they're saying that why this happens is because there's abnormalities in the currents flowing between the nerve cells in the brain. In your brain, there's electricity. In your body, there's electricity. There's electricity flowing now as I'm speaking. Electricity flowing as you're watching this video. Electricity flowing all the time. Basically, what happens is in the brain, it's like a current. There's like a circuit, by the way. Yeah, my bad. It's like a circuit flowing in your brain. And why you get depression and anxiety is because this circuit is starting to slow down, and basically you're just like, hey, you're not feeling happy anymore. Your dopamine receptors aren't like functioning. Hey, until you're starting to get sad. Your circuits aren't flowing. They're not circuiting, if you get what I mean. So what happens in TMS is they basically come and they get you wear coils, okay, these current carrying coils, and since it's like really rapid currents, okay, they produce a variable magnetic field, and they produce eddy currents. I think what eddy currents are, let me search this up. Basically, yeah, okay, an eddy current is just a current made by a varying magnetic field. So it's these rapidly changing coils have current carrying coils. The current rapidly changes, which causes a variable magnetic field, and that variable magnetic field makes more current, generates eddy currents, and basically that disrupts the abnormalities of the currents in the patient's brain, because there's a force of the rapid change, which causes a magnetic field and an induced eddy current, and this eddy current goes to the brain and starts kind of stimulating the circuits in your brain to go like, yo, work, come on, you don't have depression anymore. Okay, that's just how it works. Which of the following can change the maximum current generated in the brain? The frequency of the current oscillation in the helmet's coils. Oscillation is the number of loops. Okay, one oscillation is one complete revolution. Okay, so if you have more oscillations, there's more revolutions. The magnitude of the RMS current in the helmet's coils. By the way, just so you know, I don't know why I didn't explain this, but the current used in all your houses, the current used in your phone, the current used on the device you're watching this video on, the current used in any electrical appliance on our planet uses VRMS. It doesn't use Vmax, because if it uses Vmax, the electrical appliance will explode after 1 minute or maybe even 5 seconds. Okay, so it uses VRMS because VRMS is kind of a balance between Vmax and V0, but it's not in between them. It's not direct, and it's not in between them because sorry, not from Vmax and V0. It's between Vmax and V minus max, because you know it goes like this, right? Here is Vmax, and this is V minus max, right? Like negative max over here. So it doesn't go here because in between them that's 0, and we don't want 0. So what they did, they were like, okay, divide by radical 2. Okay, there is a proof for it. It's in the book if you want to read it. But that's what VRMS is. So into the actual voltage that reaches your device is the VRMS. If you increase the RMS, then obviously there's going to be more magnetic field. Okay, so that's also correct. The proximity of the helmet to the scalp. Proximity means distance. How far the helmet you're wearing is from the scalp or whatever. In other words, their head. Okay? Now we're trying to affect our brain. So how far it is from the brain, obviously, will change the amount of current generated in the brain. The temperature in the room, no, we never spoke about temperature. We never spoke about duration. Okay, duration might be something else, Okay, but the magnitude, the maximum current generated in the brain, we don't care about that. Okay? وكمان by the way, they were talking about the maximum current generated in the brain. Even without knowing what I told you about the RMS, if you change IRMS, you're changing Imax, right? Because IRMS is equal to Imax over root 2. So if you increase IRMS, Imax will also increase. Okay? Okay, there's a lot of talking in this, a lot of yapping in this recording, but I have to. A single conducting loop is rotating in a magnetic field at a constant frequency. Okay, the expression for the current in the loop is equal to I equals 14.1 milliampere sine 16 pi rad per second t. The RMS current in the loop to the nearest whole number is what? Not 14.1. People say, why is it 14.1? No, the formula doesn't say. The formula says Imax sine 2 pi f t. T small, huh? It doesn't say IRMS. No, it gives you Imax. So this 14.1 is Imax. And I want IRMS. How do I find it? I do Imax divided by root 2. And when you do 14.1 divided by root 2, you get almost 2, which makes sense. Because earlier we found 14.1 as... Anyway, you get almost 10. To the nearest whole number, 10. The frequency of the current oscillations. We want f. How do we find f? We know 2 pi ft is equal to 16 pi rad t. So 2 pi ft is equal to 16 pi rad t. T with t, pi with pi. 16 divided by 2 on both sides, you're going to get f is equal to 16 over 2, which is 8. The unit for frequency is hertz. Okay, please, ما تلخبط فيها. 18. The diagram below shows the EMF induced in a loop rotating in a magnetic field. At t equals 0 seconds, the surface of the loop is what? At t equals 0 seconds, it's maximum, right? When it's maximum, what happens? D flux is max when it's parallel, right? And then, at t equals 15 seconds, the flux is equal to 0. Because remember, D flux and EMF are the same thing, because EMF depends on the change in flux. So if EMF is 0 and the change in flux is 0, when is the change in flux equal to 0? When it's perpendicular. Okay? If the resistance in the loop is 0.08 ohms, then the RMS value of the current through the loop to the nearest integer is what? Okay, this is very easy. The resistance is equal to V over I. So I is just equal to V over R, right? we're talking about the RMS value of the current. So do I use Vmax or do I use VRMS? I have to use VRMS, right? So I need to use IRMS. If I'm talking about IRMS, I need to also use VRMS. Resistance is resistance, it doesn't change. It's like VRMS, how do I calculate it? I can find Vmax, it's from my graph. It's Vmax over radical 2, so 10 over radical 2, right? So remember, this is in millivolts, huh? You can check. The unit is millivolts, it's not volts, okay? Millivolts. So 10 over radical 2 divided by the resistance 0.08, and you should get, like I got in my calculator, 88.3 to the nearest integer 88. Remember, the unit is milli because we're using milli. If they wanted it in amperes, you have to divide by 10 to the power. You have to divide by 10 to the power of 3. Okay. Question 19. Oh, that's a nice, easy question. Okay. Arrange the steps describing the function of an induction cooker. Again, guys, we never took this stuff. Like, I don't remember learning induction cooker. But let's see. An alternating current is passed through the coil of the cooker. The coil generates an alternating magnetic field. The magnetic field generates eddy currents in the pot. Again, eddy currents, they're the ones that cause the rotations and like forces, okay? And since it starts rotating, the currents in the pot heat it up. Okay, I guess you can memorize this. But eddy currents is anything due to a variable magnetic field, okay? We're done for this recording. Thank you so much for watching. Please don't forget to solve the grids. Please solve them. And good luck. I will send this file. And this one, I think, no, because this one, half of the stuff we don't need it. I'll send this file, inshallah, on our Sabbath grade 11 group. Okay, thank you so much for watching and good luck in your exam.